Okay, hello everyone, welcome back. So to recap what we have been doing, we are looking at kinematics of planar motion of rigid bodies. And so far we have knocked down two types of motion. One is translational motion. So the body essentially moves in a plane without turning at all. We also looked at pure rotation or rotation about a fixed axis. And we studied or introduced angular motion, and also we could relate that to motion of an arbitrary point on the body. Okay, now it's time to do the third or the more general version of planar motion, and it is aptly named general planar motion, which is not strictly a translation nor a rotation, and it is a general motion. A good example of it, if you want to know what it is or how it looks like, you can consider a wheel that, like a bicycle wheel or whatever, that rolls on the ground without slipping. This motion of the wheel, is a general motion because if you consider any line on this wheel, like this one, as the body rolls, this line rotates, so it doesn't stay parallel to itself, its original self. So it's not a translation. You cannot find any single point that all points on the wheel turn around that. So it's not a rotation either, or a pure rotation. So it is a general plane motion. And in general, whenever we're dealing with rigid bodies, obviously, we are dealing with some kind of rotational aspect, because otherwise the notion of rigid body isn't necessary. Rigid body allows us to study rotation. So our general goal is usually relating somehow that rotational aspect of motion to kinematics of different points. And one way to do that is perhaps use Feynman's algorithm. I have mentioned this before, that Feynman's algorithm is write down the problem, think real hard, write down the solution. And you can do that to solve these general plane motion problems. And we will see there are other algorithms that are perhaps better. But in general, this is what we have been doing in the past, and that was the notion of constrained motion or dependent motion. You can do the same thing, trying to find the relationship between some of these kinematics of different points to the rotational aspect of bodies. So now that we are on the topic of a wheel, let me solve this problem using that notion of dependent motion. So I have this wheel, I'm going to draw it. Oh, it is going to be difficult. I'm going to draw, let me see. I had, here. I never used this. I want a wheel like this. Didn't turn out. Where did it go? No. This. Okay, here is one wheel. Am I drawing another wheel? No. I want another wheel like this. Okay, good. Now I want to select it. How do I select it? Like this? No. No. Can I select it like this? Yes. Okay. I bring it here. Very good. I'm progressing. Now this. This is my ground. Okay, I made it finally. So this is a wheel. Let's say it is turning or rotating without slipping. It has some angular velocity omega. What I'm really interested in is to find the motion of the center of this wheel. Let's see what we can do. And I'm not going to use any fancy math yet. We will do fancy math later. But I want to use the notion of dependent motion. Notice that as the wheel moves, it turns, and the center of the wheel goes from this point to that point. Oh, let me see. I want to do something else. Let me clear this. I want to select that, make this red. Yes. Okay. Now this one blue. Good. Okay, making lots of progress. So the center goes from here to here. I want to relate the motion of the center to the angular velocity. And how can we do that? Well, think real hard. See what happens. As the wheel rolls, take one point here, let's call it A. And the new contact point, let's call it A prime. So before, this point A prime was somewhere here on the wheel. And as the wheel rolls, this patch that I colored it green is going to be kind of covering this area on the ground. And one other thing, before I had this line vertical, now this line has become vertical, which in my previous state was that, to A prime. What is this? Wait, when did this A show up? Oh, yes, this is A prime. In other words, as I turn this much angle, I translate this much along the horizontal line. And these two quantities, S and theta, are related to each other through this contact patch, or contact path, I should say. So the length of this line A prime, which is S equals length of A prime, which on the ground is a straight line. It is both a line, A prime on the ground, and it is a piece of that curvature, or what do we call it? Arc. It is both the length of the line and the arc on the wheel. And this one, from the arc, we know it is r times theta, theta being in radians. The radius is r. So now, there you have it. You have a relationship between linear kinematics of the point, the center of the wheel, to its angular motion. Let me write it again. S is r theta. And you can take multiple derivatives. S dot, which is V of the, let's call the center G. V of G is r theta dot, or we have another word for it, r omega. Oh, not omega dot, omega. And take another derivative. S double dot, we call it acceleration of G, is r theta double dot, another derivative. We have a name for it, r alpha. So just by logic and geometry and thinking that what rolling without slipping means, we could relate the kinematics of the center of the wheel to its angular motion. Well, obviously this is not something you can do or you're willing to do in more complex problems. we will see more systematic and foolproof ways to tackle this. I'm pretty sure I wanted to say something else here, but I don't remember it. Did I want to say something else? Yeah, okay. Oh, I wanted to say this. So if you want to go this route, the route of dependent motion, remember, you always want to find, your goal would be find a relationship between some linear kinematics and an angular kinematic. Like, you want to find a function of s and theta, or another way to write it is s equals on g of theta, either implicit or explicit function. And then if you have it, you can take derivatives to find velocities and accelerations. But yeah, in the next video, we will see a significantly better way to think about these problems and a systematic way to solve this using the other thing that we have already discussed, relative motion. So I'll see you in the next video with relative motion analysis.